Hello, and welcome to Mining Magazine's session with Parker Hannifin, From Increased Productivity to Reduced TCO, Thermal Management for the Next Generation of Mining Equipment. We'll be speaking with John Hunt, Connector Territory Manager for Parker Hannifin, and Sterling McNeil, Business Development Manager for Parker Hannifin, about their exclusive thermal management solutions. Please feel free to type your questions in the attendee questions box. Don't wait until the end. I'll be reading these questions after the presentation. Over to you.
Thank you, Jax. Hello, everyone. Thank you for joining us today. Sterling McNeil and I are excited to speak to you about the next generation of mining equipment and thermal management. Today, we'll be discussing electrification movement, energy power sources, and the impact in mining equipment, the connection between power sources and thermal management, where is thermal management critical, thermal management options, safety elements to consider, how to design the right thermal management solution for your application, and how can Parker help improve your thermal management solution. Electrification movement is all around us. The growing demand to reduce carbon footprint holds much promise for mining companies. It also creates new challenges. Those limitations include battery power, cost of implementation, willingness of industry to change, technical capability, value add, is it really necessary for the business, sourcing components, which we all know can be challenging in today's market, reliability, and effective thermal management. And with that, I'll hand it over to Sterling McNeil to take a deep dive into power options and thermal management. Later, I will discuss Parker product solutions to improve thermal management.
Thanks, John. Today we're going to review, starting with the power sources. There are four types of power sources that we will review. Renewable fuels, which enables increased use of reduced carbon options and hydrogen blends. Fuel cells, which also is renewable energy, is hydrogen fuel cells, and it can be used as a scalable source of electric power. And then electric hybrid and powertrains employs an electric drive transmission with transmission with power components, and batteries where work is stored for electrical power. Battery electric as a power source. Removing diesel engines in an underground mine improves the overall ventilation. When you remove the engine, it also improves the noise reduction from the machine, which enhances performances. Which there's enhanced performance options also with battery electric, like autonomous and potential driverless vehicles. On the other side, the con side of things to consider with battery electric is the recharge time. And then also the potential for charger malfunctions, especially when you're considering an underground mine. When looking at combustion engines, a couple of the power sources is compressed natural gas, or CNG, which is a fuel gas which is mainly comprised of methane, compressed to less than 1% of the volume to which it occupies at a standard atmospheric pressure. And then LNG, or liquefied natural gas, is a natural gas that has been cooled at a liquid state, which is liquefied, at about 260 degrees Fahrenheit for shipping and storage. Hydrogen, the process of converting the vehicle from a diesel to a hydrogen is relatively straightforward. Just by taking out the diesel components, but carry over the bottom end of the engine will allow you to make this conversion. New components which would be included would be the cylinder head, the piston combustion chamber, the turbocharger, and a fuel system. Install a different motor and replace the diesel tank with a 350 bar hydrogen cylinder. What we're going to need is in order to make this happen, is we need governments to help this industry. We have to think about a lot of the logistical challenges of getting hydrogen to very remote sites, such as gravel pits, or even other open mines. We can have local production of green hydrogen, or we have to transport it like diesel, but there are long lead times in the investment to development of the hydrogen infrastructure, and the time is moving very fastly. Hydrogen electric fuel cells. A diesel tank is replaced with an electric system that utilizes fuel cells. Electricity is produced when the fuel cell combines hydrogen with the oxygen through a chemical reaction. So everyone is aware of the formidable technical costs and infrastructure challenges. Some manufacturers, such as New Holland, has designed a fuel cell vehicle several years ago, but they have found that it's hard to commercialize, and pursuing alternative green approaches. Other companies, construction companies, similar JCB, Volvo Construction, they also believe in fuel cell and have projects that they have already rolled out today. In fact, Volvo has a dedicated fuel cell lab that they opened up in summer of 2021 in Sweden. As mentioned, fuel cells combine hydrogen with oxygen, and the chemical reaction produces the electricity. The process produces only water vapor and is emission-free. A fuel cell works like a battery, but generates its own electricity from a hydrogen on board rather than being charged externally. This makes it more feasible for long-haul transportation and heavier equipment. Another benefit is that without a combustion engine, hydrogen-powered machines are much quieter. It's a very complex and highly costly process at the moment. Packaging is the greatest challenge for a lot of OEMs because there are many components that they have to fit into a very small space. That they still need gas tanks and fuel tanks, as well as deformer and cooling devices. Hybrid electric, or as it's often referred to as HEV, combines both battery-driven electric motors and a conventional engine where the battery recharges itself using the energy from the combustion engine. We're going to review diesel and electric engines, or ICE or electric vehicles. So diesel ICE vehicles, some of the things to consider when operating these in very cold temperature zones, you have to pay attention to the powertrain, and you have to warm up the hydraulics. The airflow that's traveling through the grill could potentially be blocked by snow or ice in cold areas. So it's important to consider this when considering some of the fuel consumption, as well as using the hydraulic system to help with the defrost for the actuation. Also with a diesel and ICE vehicle, one has to remember that the after treatment of a system, because if not, you will have catalyst that builds up under the hood, which if the temperature doesn't stay at a certain level, then this could have a negative reaction on the engine. When operating in hot zones and you're cooling the powertrain system, one area you have to remember is in dusty environments, you always have to clean your piece of equipment. It's mandatory that this is done to avoid overheating of the powertrain. The working conditions that impact the machine when it comes to heat management, operating the cycle of the piece of equipment, the low speed of the machine impacts like the fan rotary speed and the cooling of the system. When considering an electrical piece of equipment, good thermal management extends well beyond the battery's use of life. We don't usually refer to a specific unit of time when talking about a battery lifespan. Instead, we refer to the battery's life cycle, which is the number of cycles of the number of charge or discharges that the battery has to perform. A battery is used, as a battery is used, a chemical changes slowly in the electrochemical cells. And as these changes accumulate, the capacity of the battery decreases over time. Where is thermal management critical? Well, when it comes to vehicle design, thermal management is often underappreciated engineering discipline, and it's becoming even more critical as the world shifts to electrified vehicles. Motor efficiency and durability are directly linked to internal temperature, and thus require active cooling to effectively manage temperatures. Electric motors need to match the performance with current diesel-powered machines. Efficient thermal management has become essential to maintain the motor efficiency, durability, and safety. Electric motors require cooling with either oil or coolant. This may vary from different pieces of equipment. Underground mining equipment, for example, requires a fire suppressant system, which is commonly found typically in line with the water glycol coolant system. Thermal management is particularly important for electronics. Heat buildup can shorten the component's lifespan. Most failures in power electrons can be attributed to the cracks in the solder layer and the wire liftoff. Thermal management is required to maintain the efficiency and lifespan of the electronics. The power modules within the traction inverters generate extreme heat as they pass electric currents through the motor. They exhibit one of the highest heat fluxes in the entire vehicle, requiring thermal management solution that enables rapid heat dissipation. Lithium-ion batteries are commonly used in electrical vehicles with advantages of high power density, high energy density, low self-discharge rate, extended life cycle, and without memory effect. However, a high energy density usually results in a higher risk of thermal instability, where a chain exothermic reaction can be triggered. Therefore, operating at an even storage temperature will affect the performances. Studies have shown that the temperature is the main factor influencing the battery aging, with a negative impact on capacity and internal resistance as well. An uneven temperature distribution inside a battery pack can lead to electrical unbalanced cells, and an electrical imbalance leads to capacity loss of the entire battery pack, and to overcharge the effective cells during charging, resulting in power loss and increased temperatures. Low temperatures typically heavily reduce the power and energy capacity of the battery and increase their internal impedance. High temperatures increase the reaction rate, which result in the delivery of higher power and improved capacity, but at the same time leads to an even higher temperature and increase in thermal load. Moreover, the additional problem caused by high temperature may be the capacity fading because of the electrolyte decomposition and the non-uniformity of the passivation layer. The main purpose of thermal management in fuel cell systems is to ensure operation within a specific temperature range. Challenges include heat rejection, heat coolant conductivity, air path management, and freezing. Heat rejection in a fuel cell efficiency degrades throughout the lifetime. The heat generation increases more rapidly than the efficiency loss. Coolant conductivity is when it becomes too electrically conductive in fuel cell operation. So if it is too high to damage, reduced efficiency and electrical shock hazards may occur. Air path management may not only control the temperature to ensure optimal temperature is achieved, but it also introduces humidity. And if considering freezing, where the water is remaining in the fuel cell that can freeze during cold ambient parking in the blockhead, and it won't receive enough H2 and O2 gas to supply that it needs, which would lead to starvation. To combat overheating of mining equipment, thermal management is essential, specifically active thermal management. The main difference between them is the primary objective. Some have been developed to cool while others stabilize temperature extremes, but which is a better method? Let's discuss the different methods. First one is air. The air circulates across the battery pack or engine, typically from an AC unit or drawn in from the outside. This cooling method utilizes convection to maintain stable temperatures. The next one is liquid. Many researchers have proved that liquid cooling is almost one of the most promising cooling methods compared to air cooling, although the latter advantages in the production cost, utility rate of space, structure complexity, and so on. The results show that the maximum temperature rise and the maximum internal temperature difference of the battery system in the dual inlet and dual outlet liquid cooling system are significantly reduced, and the heat dissipation efficiency is improved compared with the single inlet and single outlet flow path. A refrigerant thermal management-based system consists of a condenser, evaporator, and a battery unit, which is supplied by the refrigerant circuit of the air conditioning system and controlled separately via valves and temperature sensors. A phase change material is a material that releases and absorbs energy to provide heat and cooling to thermally sensitive batteries such as lithium-ion and lithium polymer batteries. Some of the pros and cons. Some of the pros: reduce heat, long life cycle. Some of the cons: low thermal conductivity and leakage. Next is a heat pipe. A heat pipe is a high efficiency heat transfer device that meets the requirement of improving the longitudinal heat transfer and brings very small change to the structure complexity. A heat pipe can be applied in a battery thermal management system. A heat pipe's cooling device is in the center of the battery pack and can effectively reduce the operating temperature and strain of the lithium battery. A recent publication in the Journal of Energy Storage shared an experimental study on the feasibility of heat pipes in the thermal management of electrical vehicle batteries. There are 4 copper tubes between 2 battery-sized cylinder heaters, and the condenser part is cooled by a water bath. The heat pipe can be used to recover the latent heat of the phase change material with an appropriate melting pot at the end of each cycle to ensure that the battery temperature is low when it is used for a long period of time. The heat pipe battery thermal management system also introduces a combustion of natural convection, fan cooling, and wet cooling methods. The system can control the temperature of the battery pack within an appropriate temperature range with a minimum energy and water spray cost. Safety elements to consider. Thermal management is paramount in the battery safety. Battery designers intend for the batteries to be used within a certain operating conditions, but they plan for abuse conditions. The real world is unpredictable and complicated. Intentionally or unintentionally, batteries are subjected to abuse. Abuse conditions refer to any situation where batteries sustain damage or operate outside of a design condition. Leak detectors minimizing impact. Leak detection is an absolute necessity for monitoring the battery health of an electric vehicle, whether the vehicle is on the road or charging. Electric vehicles possess substantially more complex coolant control systems than diesel engines because they typically utilize both refrigerant and cooling to control the temperatures of numerous components. Eliminate thermal runaway. Thermal runaway is also called thermal explosion in chemical engineering. Thermal runaway is the most often caused by failure of the reactor vessel's cooling system. Failure of the mixture can result in localized heating, which initiates thermal runaway. Similarly, in flow reactors, localized insufficient mixing causes hot spots to form, wherein thermal runaway conditions occur, which causes violent blowouts of the reactor contents and catalyst. Incorrect equipment, components, insulation is also a common cause of thermal runaway. Many chemical production facilities are designed with high volume emergency venting and a measure to limit the extent of injury and property damage when such accidents occur. Lithium-ion batteries have been widely applied in electric vehicles and hybrid vehicles for energy density, absence of memory effect, and long cycle of life. However, it forms a severe challenge to the battery safety because of the fast increasing demands of electrical vehicle performance, such as high driving mileage and fast acceleration. This is due to the battery temperature will keep rising with the space constraint and time accumulation during the charging and discharging process. When it exceeds the safety temperature range of -20 to 60 degrees C, thermal runaway may be caused, and the potential consequences is a fire. Some of the best practices to use to avoid thermal runaway are as follows: regularly scheduled battery maintenance, continuous monitoring of battery cabinet temperature and or individual battery terminal temperature, and systematic review of the history of the battery data, a good thermal management system, and how to manage heat dissipation. Battery packs need to have active thermal management controlled by battery management systems, or BMS. For instance, for example, an American-based EV manufacturer with locations in California and Texas uses a glycol-based liquid coolant, the same type of media found in typical car radiators, to both heat and cool the pack to keep the vehicle from optimum operating range. Most thermal management systems use a cooling system with forced convection to maintain the optimal temperature and optimal temperature range for the batteries. There are a number of materials that, once cut and functionalized, are capable of eliminating calories generated by electric battery cells. However, it should be kept in mind that a good electrical insulator is rarely an excellent thermal conductor. Selecting materials that can dissipate heat is therefore a matter of compromise between dielectric properties, thermal class, mechanical characteristics, cost, and any other constraint defined in the battery specification. How to specify the right solution? So everybody wants a compact, lightweight battery pack, but a reduced size and weight often comes at a cost of highly efficient thermal management measures. You can't fit a liquid cooling system into a smartphone, for instance. Likewise, no one wants to use a battery power to run a thermal management system. Minimizing power storage is a common goal, which again comes at the expense of efficiency. Air and liquid cooling seems that they can be highly effective, but they consume battery power. Finally, versatility is a useful feature. Some batteries need to work well in wide range of temperatures. For example, batteries for an electric vehicle need to function properly in extremely hot and extremely cold conditions.
Thank you, Sterling. That was very informative, a lot of information there to cover. So to help you keep your equipment operating efficiently, Parker offers a full portfolio of thermal management products that are proven to absorb and redirect heat away from critical parts. Parker's Easy Form hose provides extreme flexibility with easy and quick installation of coolant, water, and oil. This hose is a suction and return line, and it minimizes the need for costly made-to-order pre-formed hose and metal tubing. We've all seen those radiator hoses on our cars and trucks. This hose can be basically twisted, bent, turned in any direction. This reduces installation time, provides rapid delivery from stock, and does not require dedicated inventory for those pre-formed hose assemblies. Parker's Push Lock hose is a multi-purpose hose line that features the widest fluid capability, application range, and size range in the industry. Assemblies can literally be made in seconds without the need for clamps or special tools. And in applications where a number of hose carries different media, Push Lock colors reduces timely tracing of the lines. In other words, this hose comes in red, black, blue, green, etc. And if you're running different medias through each line, it's easy to track on the machine. Push Lock has the highest working pressure in all sizes, making it the most versatile general purpose hose available. Next is Parker's polyethylene tubing. This tubing guarantees excellent durability due to its stable, long-term mechanical properties, made with virgin material designed for demanding high-performance environments, enhanced dimensional stability, uniformity, and long-term strength. And this comes in a variety of colors as well, as you can see in the picture. Parker's ECH hose, or electronic cooling hose, is new, and it's engineered to handle heavy-duty, high-pressure battery electric mining machine applications. This advantages are minimized weight and pressure drop, compatible with Parker VA fitting solution, thermal formable assemblies, chemical-resistant polymer liner, and it's fiber reinforced. Parker's NSA and NSI dry brake couplings. These couplings are designed for battery cooling application. They provide minimum fluid loss during connection compared to minimal pressure drop and no inclusion of air or dust during connection. You want everything to be as clean as possible, and these dry brake couplers give you that benefit. These are quick and dry connection, disconnection, can be used for cooling of onboard electronics. They have a non-spill design. The internal design is for water cooling. It minimizes pressure drop and is available in aluminum, brass, and stainless steel. Parker's Rectus Series 200 KL is only in stainless steels for block and plate assemblies, has a nominal diameter for fluid handling applications in sensitive environments, normally up to about 15 bar. These are also dry brake, no spillage and minimum dead space volume, no air inclusion when connecting, and they tolerate deviation in an axial alignment when installing. It makes it very easy to connect and disconnect. And our liquid fit push-in fittings. These liquid fit Parker fittings offer a stainless steel adapter that ensures reliable and compact connections combined with excellent robustness. These liquid fit fittings offer a full flow efficiency, no need for tools, glue, crimp, or weld. They're very economical alternative to metal connections. They are 100% leak tested in production and 100% dated in production. And Parker Car Stick is a fully integrated cartridge that provides an instant connection between the housing and the tubing, which increases energy efficiency and productivity. The car stick allows the design of custom manifolds while reducing leak points. The benefit includes an integrated seal for best-in-class productivity saving, a compact design for space saving. It's a very economical alternative to threaded connections. It's also 100% leak tested in production, and the date code is on the packaging. In Parker's electric motors with integrated cooling, we call them the GVM, as a high efficiency motor with the widest speed range based on optimized rotor design, along with patented cooling system that enables a higher continuous operating performance and reduced thermal loss. These motors are high efficient and lightweight, high power density with a reduced footprint, lower energy consumption, extended vehicle range, and reduced battery size requirements. And finally, our fans, drives, and coolers. Parker's QDC Air Fluid Cooler Series offers a unique cooling solution with a brushless fan drive, which is ideal for electrified mining machinery. The benefits are high density and low pressure drop. These are efficient, robust, and a very compact design. Integrated inverter controls the rotation speed with a standard PWM signal to reduce power consumption, reduce noise pollution. These seamlessly integrate with an ICANN controller and super easy to maintain. Thanks again for joining us today, and we're happy to answer any questions you may have.
Great. Well, thanks very much for that. We have a question from James Costin. He says, on the liquid cooling system, is there a particular type or composition of liquid that is typically used, and what is the best liquid coolant?
Yeah, here, I'll take that one. What we're finding is, depending upon the application, it's water glycol, it could be refrigerant, or there could be other types of water-based glycol types of medias out there. But there's no standard today that calls out that it needs to be one type of liquid. So you'd have to, depending upon your application, figure out which one's best for you.
Which thermal management technique is considered to perform the best with the highest heat transfer efficiency?
Liquid cooling has been, I'll go back to the liquid cooling. That's been the one technology that's been proven for the higher heat to be used to find that to be most efficient in cooling battery electric vehicles and battery packs.
Great, thank you. Paul Simpson has a question. He said, can I get more information on the liquid-cooled electric motors and what is their IP rating?
Yes, we can follow up afterwards. There is a microsite Parker has that will include to where you can find all this information.
Fantastic. And Gary Wayne has a question. Are hydrogen fuel cell vehicles being used in surface mining?
I don't know the answer to that. John, you are more at the mines physically than I am.
I mean, it's definitely being discussed. Equipment manufacturers have played around with this. I think you mentioned in the presentation that Volvo is doing a lot of work, and CAD is also doing some work. I have not seen any yet, but I do know it's being discussed for surface mining. Again, you mentioned, Sterling, the cost is probably the biggest obstacle.
Okay, great. Maybe we can talk about what is GPU thermal throttling?
Well, thermal throttling protects the hardware. So your computer components, like your central processing unit and your GPU, and even the memory modules, that they all produce heat. So under heavy loads, they produce a lot more heat, and so which ultimately that can lead to them being for them being too hot, too hot, that then when they won't be able to perform to the performance that they need to.
Great, thank you. And how about this one? Is immersion cooling a good option for mining?
I can take that one, Sterling. I think they're ideal for mines who wish to extend the lifetime of the machine. It helps control noise, heat, and it's very efficient. I think that's definitely a great option.
Great. And can you ever combine cooling technologies for thermal management?
So it is common to have like a hybrid type of system. We are seeing a number of systems that have a hydrogen fuel cell, and then they have a battery electric, because you're using the hydrogen fuel cell to power using the heat from the fuel cell to power the battery. So therefore, you're having a combination of two different types of technology. And then within that, you have to have the thermal management to maintain the temperature range of the components. So there you would have your combined technologies utilizing thermal management.
Great. What temperature should the mining rig be set to?
I think it's definitely a range for your piece of equipment, but an optimal level is normally 70 degrees Celsius to 75 degrees Celsius.
And how do I select the right fluid coupling with a high flow and a low pressure drop?
Okay, I could take this one, John. So the fluid couplings, the fluid couplings are in a hydrodynamic devices that transmit the rotating energy between the drive shaft and the prototype belts and the motors and the conveyor belts. All factors need to be considered when selecting the right type of fluid couplings. You need to look at the power levels, how often you're going to need to fill those. Do they need to be controlled filled? And then what is the thermal performance? So the most efficient battery thermal management system, for efficiency within the battery thermal management systems, we're seeing quick couplings. A lot of them are being used. So going back to those, the different types of couplers, the NSA, the NSI ones, and the dry brake, the KLs, it really comes down to size, and then go through your size, your temperature, your application, your media, and your pressure to help select the overall proper product.
And what are the main thermal management challenges with electric commercial vehicles?
So unlike internal combustion engines vehicles, one of the things they don't have to worry about is heat loss, because most of the heat is at the fuel cell and the powertrain side. And so the heat would be rejected via the coolant circuits, and the lower temperature levels. The ICE vehicles operate at a lower temperature level. Therefore, a fuel cell vehicle requires a higher cooling performance than an ICE vehicle. So that's where that's one of the main differences between a internal combustion engine and a battery electric. Sorry for the tongue twister explanation.
That's all right. Are there any specific considerations to enable efficient, fast charging?
I think the UL has developed a comprehensive test to determine mechanical, physical, electrical, characteristic properties to ensure that chargers are being made safe using their the proper equipment, proper voltage, etc. So I do think there is a standard in the industry. I don't have those details in front of me, but I could circle back.
Sure. And where do you see the mining? This is another question from James Costin. Where do you see the mining industry going in the future? Assuming that there is a transition away from diesel-powered engines, is there more potential in battery electric or hydrogen cells, or is there another technology that has more potential?
John, I'll start, John. I think you need to look at it at two separate ways: your open pit as well as your underground. Underground, from a safety standpoint, you have to consider having the battery electric because, well, you already have it's going to require a fuel suppressant system to be tied in with the water glycol loop. So, which has a little more safety features than, say, the hydrogen, which doesn't have that same requirement. So, that would be one way that you could see it going more of a battery than it would be hydrogen. But again, that's just underground. John, do you have any input for open pit?
I would agree, Sterling. I think underground battery is definitely the easiest next step, and probably for open pit it would be the same, just because the technology's there already. We're getting more power out of the batteries. Pumps are running at lower volts and pulling less power. I think the hydrogen definitely is a great technology, and as it becomes more and more technologically advanced, I think you'll see more and more equipment manufacturers leaning that way, just for the ease of not having to charge and not having to return that piece of equipment to a charging station daily or nightly or whatever it may be.
Great. Is active or passive cooling better?
So the choice between active and passive is going to really come down to your economic trade-offs. Active cooling results in higher battery performance, but it also costs more to do. So again, it goes back to really a cost point.
Okay. And how do you choose the right tubing material for a liquid cooling system?
Maybe I get to plug stamped on this one. I mean, I think everyone knows that acronym that works in our industry. So size, temperature, application, medium, pressure, definitely are things to consider when choosing the right tubing for or the right hose or the right anything for the application. So just remember that STAMP acronym, and it's well known in our industry.
And with the fittings that you recommended, what is the compatibility with the various thermal management liquids?
Sterling, I think you're still on mute.
Can you hear me now? Yeah, the Liquifit product that we recommended, it's compatible with several liquids. A lot of those being water glycol based with deionized water. So as I mentioned, that's a lot there. So tap water, water glycol, and then the products have also been qualified with Novak 7000, that the product that 3M makes. as well as it's being tested with Cal E at the moment from Dow. So those would be the medias that's compatible with those.
Great. And I think this is our final question here. Are there any specifications regarding thermal management?
Yeah, there's a couple from UL. So there's UL 94 V-0, which that's the most common one. And then another one that you'll find is UL 94 HB, Harry Boy. That would be the second one, but the V0 is the most common.
Okay, great. Well, thank you very much for that. That seems to be all of the questions that we have. So I want to thank John Hunt and Sterling McNeil again. It was very, very interesting from Parker. And thanks very much for tuning in.